Hello and welcome back to this course. So last class we were discussing about the characteristic curve for fuel cell as well as electrolyzers, and coming to fuel cells we started with the enthalpy of the reaction. So we have considered this conventional hydrogen oxygen converting into water, the conventional reaction for which the enthalpy is 286 kilojoules per mole. And so when we convert this into the corresponding potential, we get 1.48 volt, which is called as thermoneutral potential. Then of course this is the maximum energy content, which also takes into account the combustion energy as well as the translational and rotational energies. However, we have to also reduce the, or rather subtract the loss due to entropy, after which we get the energy available at our disposal as 237 kilojoules per mole of hydrogen. So that if converted into potential, we get as 1.23 volt, and this 1.23 volt, as we can see, is called as the reversible cell potential at standard temperature and pressure conditions. However, in real practice, the fuel cells or electrolyzers, or if we restrict our discussions to fuel cell as of now, these cells are operated at much different temperatures and pressure ranges. Typically, if it is a low temperature polymer electrolyte membrane based fuel cell, it is typically operated around 670 degrees and pressures are typically 5 to 10 bar. And since these are the operating conditions far different from the standard temperature pressure conditions, there is a deviation that we observe in the potential when there is no current flowing. So that potential is called as Nernst potential. We have already seen how a Nernst potential varies depending upon the temperatures as well as pressures. Moving on, we also have to sometimes include or consider loss due to fuel crossover, as I was discussing last time, when we have this electrolyte sandwich between the two electrodes, that is anode and cathode, and when we have hydrogen supplied to this anode. So instead of hydrogen getting oxidized to protons and electrons, this hydrogen, being the tiniest molecule, it basically diffuses through this electrolyte. It due to the macro pores that are available in the, or present in the electrolyte, and it gets oxidized at the cathode itself, here itself. So this is highly unfavorable reaction, and since we are losing the fuel unnecessarily on the cathode side, that is why this loss is called as loss due to fuel crossover. So fuel is being crossed, or it is getting crossed, and the reactions take place at different electrodes. So this loss is, that is why called as fuel crossover. So ultimately we are able to see the potential across the terminals of the fuel cell, and that potential is called as open circuit potential. Why is it called as open circuit potential? Because because as of now we are not drawing any current from the circuit. So current drawn in the circuit is still 0. And so when we proceed with the current that we want to draw from the circuit, then the losses come into picture. Theoretically, we expect the potential to remain constant, I was discussing last time. So this is the potential that we expect to maintain no matter how much current is drawn, or even if the infinite amount of current is drawn from the cell. However, in real practice it does not happen. So the performance curve typically takes shape like this, as we can see. And why it takes this shape? Because there are three major losses that take place in this electrochemical system. First one is, as we can understand, it is a activation loss denoted by eta subscript act, and as we have discussed, this is basically energy that is needed to kickstart the reaction at the respective electrodes. So for example, if you are talking about hydrogen oxidation at anode, we will also expect activation energy for this reaction, and if we are talking about the other reaction that takes place at the cathode, that is half mole of oxygen plus 2 moles of protons plus 2 moles of electron giving water. This reaction also needs an activation energy. Combined these two activation losses, so I can write this is eta activation subscript anode, and this is eta activation cathode. So these two activation energies together give rise to total activation energy. So this is activation of anode plus activation of cathode. So similarly, in the ohmic zone we have typically with respect to electrolyte, there is only one ohmic resistance coming from the electrolyte, which is common for both the electrodes. So, eta ohmic for the electrolyte remains the same. However, in case of, like we were talking about the other charge species, for example, the electron has resistance on the anodic side as well as it has the resistance on the cathodic side. So, together it also acts like a resistance to electrons. So, those two resistances have to be summed up in order to find out the complete ohmic resistance. And coming to mass transfer, I think we were discussing about the mass transfer as well, and this is what I was discussing, that let us take an example of bucket which is full of water, and we are supplying water using this tap which is on the upper side of the bucket, and we also have connected one tap at the bottom of the bucket. Let us say we have this bucket and we supply water. So, if you do not take any water out from the bottom tap, the level remains the same, water level remains the same. So, and if you start taking more and more water out, so as we can see, the water level will eventually go down. This problem can be overcome by increasing the flow rate that which is supplied to this bucket or at which we are filling this water. And if we go ahead and start taking water out from the lower tap, the water level is eventually going to go down. So, this rather example we can relate it to our electrochemistry, wherein the water level in the bucket can be considered as the potential of the cell, whereas the water that is input to the bucket is just like your fuel supply, that is hydrogen in our case, and the water that we are taking out from the lower tap is the current that we are drawing from the cell. So, with this we can understand that in case of fuel cell, even if I consider the first case, that is we are supplying water as 1 liter per minute. So, if I maintain the flow rate of hydrogen as 1 liter per minute, let us assume that we are going to get performance curve like this. So, in order to avoid this third zone, that is mass transfer zone, what we can do? We can increase the flow rate, for example 2 liter per minute. So, in that case, as I have already mentioned, this flow rate of fuel that basically is supplied to the cell affects, or rather it has its impact only particularly in the third zone. So, even if I increase the flow rate, we cannot expect fuel cell performance to curve to go like this. It will not happen like this. So, what we have to do, or what happens in the cell, is your activation, and let me draw it from the different color. So, as we increase the flow rate of the fuel, the performance curve goes something like this. It is almost parallel, it rather matches the the previous performance curve. However, when it comes to the third zone, third phase, it slightly we see enhanced performance because we have increased the flow rate. So, now we have enough fuel at the interface of electrode and electrolyte. So, we observe a less mass transfer loss. We can even go ahead and increase the flow rate. So, let me write this is for, let us say 2 LPM. These are merely examples, and this one is, let us say, for 1 LPM. So, let me go ahead and draw for, say, 3 LPM. So, what it means is basically, even if we increase the flow rate to infinite liters per minute, I cannot draw an infinite amount of current. So, this is for, let us say, 3 LPM. This is an example. So, what it means is, no matter how much flow rate we supply, we cannot draw infinite amount of current. Let me write that down. So, amount of current drawn from the fuel cell is limited with respect to fuel flow rate. This is a very important conclusion, and that is why the current that are drawn they are finite, and they are, although they are dependent on the flow rate, but that flow rate has a, or rather increased flow rate has a very limited impact on the current increment. So, we can see the current that is increased from 1 LPM to 3 LPM is finite. So, that is why we have to be very careful while we supply the fuel to the fuel cell, because excess flow rate of fuel to the fuel cell ends up in the losses in the efficiency, which we will see in the today's class. And before I move on to the actual efficiency calculations, let us quickly have a look at the electrolyzers as well. So, as we have discussed this before, the electrolyzer performance is exactly sort of opposite with respect to fuel cell. We can very easily compare both of them, and the electrolyzer also has 3 zones, which is activation zone and ohmic zone and the concentration zone. And so, since it is a load, electrolyzers are load, we cannot actually measure any potential at its terminal. We have to supply the energy, and in order to do that, we have to first find out if we are expected to run an electrolyzer at a specific temperature and pressure. We have to find out what will be the minimum potential to break the water, and that can be easily found out using Nernst potential, and that Nernst potential will define the start of the curve. So, for example, we discuss about this 80 degrees temperature, where we saw that the Nernst potential was approximately close to 1.15 volt, and that underlines that 1.15 volt will be the starting point of this curve, wherein the curve will go something like this. So, how that curve goes depends on what materials are used in the electrolyzer, what is the catalyst, what is the electrolyte type, what is its conductivity, what is the surface area of the catalyst, and of course, the temperature of water that is supplied, and the flow rate. So, with that we will move on to the efficiency calculations. For now, we will restrict ourselves to calculation of the efficiencies for fuel cell. So, let me write fuel cell efficiency. Right. So, let me take this IV curve one more time. So, we have, let us say, open circuit potential is roughly 1 volt, and we will find out the efficiencies at 3 different points. So, these are my 3 different operating points. This is at 0.8 volt, and this is at 0.5 volt, and this is at 0.3 volt. So, first and foremost, the efficiency that we need to find out is the thermodynamic efficiency. Which is nothing but the ratio of reversible cell potential E naught by thermoneutral potential. So, let me write this up. This is reversible cell potential at STP divided by the thermoneutral potential, and we have seen that both of these figures are constant for hydrogen oxygen fuel cell, which is, so this is considered H2O2 fuel cell. So this is 1.23 divided by 1.48, which comes roughly around 83%. So this is my thermodynamic efficiency, which is denoted by eta Th subscript Th, and it is a constant number. So what it means, basically, out of the maximum energy available, which is 286 kilojoules per mole, that is the enthalpy, we can expect only 83% to be available for our other usages. So that is what the thermodynamic efficiency means. Then we have, let us go to the next type, that is the voltage efficiency. So that is denoted by eta voltage, and this is nothing but ratio of the operating potential of the cell divided by the reversible cell potential at STP. So since the reversible cell potential at standard temperature and pressure conditions are, or rather is considered as a very standard number, reference number, hence the voltage efficiency is always calculated with respect to this E naught. So if I take the example of this one, wherein this is our first operating point, this is second operating point, and this is third operating point. So in the first case, our voltage efficiency, voltage is at 0.8 volt, next operating point is at 0.5 volt, and the third one is at 0.3 volt. So I can write voltage for the first operating point as 0.8 volt divided by 1.23. So this is my reversible cell potential, though this comes close to 65%. Similarly, I can find out for the rest of the 2 points, operating points. So voltage efficiency for second point is, the operating point is at 0.5 volt divided by 1.23. So this number gives us efficiency close to 40%, and third point, wherein the voltage efficiency at 0.3 is around 0.3 volt divided by 1.23. This will give us around 25%. So as you can see, the voltage efficiency is directly proportional to the operating point. Where is our operating point? If it is close to, as we can see in this case, if it is close to the open circuit potential, in other words, if you are operating at in the low current density zone, or in a zone where low current is being drawn, so voltage is higher, subsequently the voltage efficiency will also be higher. If you move further, if you start drawing even slightly more current, the voltage will drop, and correspondingly the voltage efficiency will also drop. Coming to the third point, so wherein the current that is drawn from the cell is even higher, relatively even higher, so the voltage is low, so subsequently voltage efficiency will also be low. So in other words, the voltage, voltage is the operating point is the one that decides the efficiency, voltage efficiency of the cell, and higher is the operating potential, higher will be the efficiency. And it goes, or rather follows this same line as we can see in case of performance curve. So efficiency also follows a similar trend with respect to voltage. So we have one more efficiency, that is called as fuel efficiency. This is denoted by eta fuel, and this is actually the amount of fuel required to the amount of fuel supplied. So, what it means in other words is the amount of fuel that is actually supplied to the cell is far more that compared to what is the theoretical requirement of the fuel. So, we will eventually find out how we can find out the theoretical requirement of a fuel. So, let us go ahead and find out the amount of fuel required. This is also termed as a theoretical value. And how do we do that? It is m dot for hydrogen, let us see, and the unit is in liters per second, and this is nothing but I n V by Nf. Now, what is I n V? We are already familiar with Nf, this term Nf. What is I? So, let me write where I is the total current flowing in the cell or the stack. Okay. So, this is in amperes. What is the N? N is capital N is the number of cells in a or in the stack. So, it is a constant number. It can be, a stack can contain 2, 3 or even 5 cells or 10 cells. So, that number in a cell determines the capital N. V is your molar volume. Molar volume, which is 22.4 liters per mole. It is a constant number at STP. So, any gaseous product will have a volume of 22.4 liters if it is contained at STP, and N and F are already known. So, let us first find out the unit, whether we get the flow rate of hydrogen in liters per second. So, m dot H2 is I n V by Nf. So, I is in amperes, which is coulombs per second. N is just a number of cells. So, it is a unitless quantity. Volume is liters per second. So, let me write liters per mole, and this N is a number of moles of electrons. So, it is a constant number, and F is your Faraday's constant, which is 96,485 coulombs per mole. So, if we look at this mole gets cancelled, coulomb also gets cancelled. What we are left with is liters per second. So, m dot H2 will have unit of liters per second, and which then we can eventually convert this flow rate into the mass flow rate, and provided we know the density of hydrogen at particular temperature, which is almost constant. The density of hydrogen is 0.089 kg per meter cube, right. It can also be written as 89 gram per meter cube, or it is 89 milligram per liter. So, let us go ahead and see how we can solve and find out the flow rate for the hydrogen. We have to, what we need to ensure is, this is the theoretical value. So, amount of fuel that we are supplied, amount of fuel that is supplied to the cell should be always greater than the theoretical value. So, in other words, m dot H2 actual should be greater than m dot H2 theoretical. So, theoretical we have just found out it is can be found out if we know the current flowing in the cell or the stack, and if we know the number of cells in the stack, we can find out the flow rate that is required to maintain that amount of current, and the actual flow rate that should be supplied to the cell should be greater than this theoretical value. So, let us quickly take an example. So, let us say I have a cell that is having current of roughly 25 amperes of current is flowing through that cell. It is a single cell. Let us find out the flow rates of hydrogen and oxygen as well. So, it is a very straightforward numerical. We have been given the amount of current that is flowing, number of cells. So, let us go ahead and find out m dot H2 is I n V by Nf. So, I is the 25 amperes of current, number of cells are 1, volume is 22.4 liters. It is an hydrogen oxygen fuel cell, I forgot to mention that, H2O2 cell. So, N is 2, where F is Faraday's constant 96,485, and this leads to, if we calculate this comes close to 174 liters per minute, okay, milliliters per minute. And how do we find out mass flow, volume flow rate of oxygen? So, if we look at this, we can also use the same formula, which is I n V by Nf. However, in this case, the what differentiates from the hydrogen is number of moles of electrons that are involved. For oxygen, it will be 4, and Faraday's constant remains the same. So, in this case, it will be half of what we have just calculated, it will be somewhere around 84 milliliter per minute. Or in other words, we can also do the small trick. If you know hydrogen and oxygen combine together to form product water. So, if we are supplying 1 mole of hydrogen, half mole of oxygen is sufficient. So, whatever is the flow rate or the mass flow rate or the volume flow rate of hydrogen, half of that is sufficient for oxygen to be maintained. So, in that case, so we can still get roughly around 84, or we can even go ahead and just divide m dot O2 is basically half of m dot H2. So, this also comes around 84 milliliters per minute. So, that is how we can go ahead. So, once we have found out flow rate, theoretical flow rate for this type of fuel cell is around 174 milliliters per minute. So, let me write that down. So, the cell should be supplied with 174 and 87 milliliters per minute of hydrogen and oxygen respectively. But like we discussed earlier, this m dot hydrogen actual should be greater than your theoretical value. So, this is, we know this is around 174 milliliters per minute. So, what should be our actual flow rate of hydrogen? So, it should be more than 174. We can even make it as 175, but that delta increment, that increment that we are doing with respect to actual mass flow rate should be slightly considerable. So, in and around we can keep it at around 225 milliliters per minute. So, if once we fix the actual flow rate of hydrogen, then we can go ahead and find out the efficiency of fuel, that is fuel efficiency, which is nothing but the theoretical flow rate of fuel, that is I can write fuel required to fuel supplied, which is nothing but 174 by 225. So, this comes somewhere close around 77%. So, what is that extra? What is that extra fuel that we need to supply is characterized, or it is identified by another factor called as stoichiometric factor, or it is also called as fuel utilization factor. So, fuel utilization factor, which is basically this fuel utilization factor is also called as stoichiometric factor, denoted by letter lambda, and this is exactly opposite of fuel efficiency, or I can write it other way around. So, we know fuel efficiency as 77%. So, my fuel utilization factor will be 1.3, roughly 1.3. So, what does it imply? It implies that so when we have fuel utilization factor as 1.3, so when the lambda is, let us say 1.3, it means I am supplying 30% excess fuel. If my, let us say, lambda is 1.2, that implies 20% excess fuel is supplied. So, this fuel utilization factor takes into account the excess fuel that has to be taken into account, so that the fuel cell does not starve and it functions well and it does not end up in the mass transfer limitations. So, that is how this fuel we have to consider. For oxygen also we can take the fuel utilization factor, but typically it is for fuel, that is for hydrogen, this lambda values typically varies from 1 to 1.5, which means maximum of 50% excess fuel we can supply in case of hydrogen. For oxygen, this lambda is typically around 2. In other words, oxygen is excessively supplied because more care is taken for the fuel, and that is how we bring it to the total efficiency, which is product of all these three efficiencies that we have considered. The first is thermodynamic efficiency multiplied by voltage efficiency multiplied by the fuel efficiency. So, once we find out all these three efficiencies, we can find out the total efficiency of the fuel cell. So, with that I will stop here and we will take on with this efficiency calculations and the further details in the next class. Thank you.